Okay, what we're going to do today is we are going to learn how to do inductor problems in electric circuits. Now, I just want to say that the capacitor problems will be done very similar in a very similar fashion, so we can use this video to also learn about that as well. Okay, so the example problem that I have for you is here. Okay, so and typically with these circuits, there's going to be an inductor or capacitor, and you can see the inductor is right here, and there's always going to be a resistor in there. Okay, the battery is located over here. I know we're used to seeing batteries with the lines, but sometimes batteries are noted like this. This here is a switch. When the switch is thrown in the 1 position, that means it's connected to the battery and it's charging. When the switch is thrown in the 2 position, that means the battery is disconnected and it's discharging. So we're going to do one charging problem and we're going to do one discharging problem. Okay, so what we have here is we're given some information. We're given information here with the resistor size, the inductor size, and the battery sizes here. So the resistor size is 5 kilo ohms, that's 5,000. The inductor size is 25 millihenries, that's right here, and the voltage is 100 volts, okay? So we need to find the circuit's time constant first, and when it's closed, we need to figure out what current is stored in the inductor at 2.5, 5, 15, 20, 30, and 40 microseconds, okay? Now, the very first step that we're going to do is to create a chart, okay? We're going to have 3 columns for this. This first column is going to have the time that we're concerned about, okay? The second column is going to have a multiple of time constant, and we'll talk about that in a second. And then this last column is going to have current, the actual current that's stored in the inductor at that time, okay? Now, the very first thing we're going to do after we make that chart is we are going to go ahead and calculate the time constant. Now, the equation for a time constant for an inductor is here. We're going to take the inductance value, divide that by the resistor value, okay? So we have 25 millihenries divided by 5,000, and we end up getting 5 microseconds. You can see that little Greek symbol right there is microseconds. So what we need to do is we need to divide each number here in the first column by the time constant, and that will tell us the multiple of time constant that we have. So if I take 2.5, divide that by 5, I'll get 0.5, so that's a half a time constant. If I divide 5 by 5, that's 1. 15 by 5, that's 3, and so on. You can see that's where those numbers come from, okay? The units are going to cancel themselves out, okay? Now what we're going to do next is we have to figure out the final current for the circuit. So the final current, we're going to use Ohm's law. V equals IR. But we have to reformat it with I equals V over R. So there's the voltage, there's the resistance, and we end up getting a final current. So when our current is fully stored in the inductor, we should get a final current of 0.02. Okay, that's called the steady state current after the inductor is charged. So steady state means it's steady, it's not changing. However, when it's charging, we have this other word called transient that we're going to use. Okay, that means it's constantly changing. It's going to grow in an exponential fashion, and we're going to use that special graph that's on our worksheet to help us, and it's on the next page. Okay. So this graph is a very general graph. You can see that I just put multiples of time constants. We can use this exact same graph for inductors and capacitors. So to use it, what we're going to do is we're going to find the multiple of time constant that applies. We'll trace up to the curve. And when we get to the curve, we're going to trace over to the side here on the y-axis, and that will tell us the value that we need to multiply the final current by, okay? So again, we trace to that we find our value of time constant down the bottom, what multiple of time constant, go up to the curve, and then trace over. So let's go ahead and do that for our problems, okay? So for a half a time constant, I'm going to go across the bottom, I'm going to trace up, and I'm going to go over, it's going to be about 0.42. So the current at that point is going to be 0.42 times 0.02, and that's going to give me 0.0084 amps, I'm going to restate it by 8.4 milliamps. For one-time constant, we've got a special value. One-time constant is going to be 0.632, and then we go ahead and do the multiplication, we get 12.6 milliamps. For 3, we can trace up, okay, and we get about 0.93. So the current's going to be 0.93 times 0.02, 18.6. And continuing on, 0.97, okay, sorry, excuse me, for four time constants, we're going to get up to 0.4, trace over to 0.97, and we get 19.4. Now, if you take a look, anything over 5 is kind of like the magic number. Anything over 5 is going to be steady state. So we really don't need to do any multiplications over 5. So since 6 time constants is over 5, we know that 100% has been reached. So that's going to be 20 milliamps or 0.02 amps. Same thing for 8. Okay, 8 time constants. That's going to be 20 milliamps as well. So now that we know that information, we can go back through these 2 slides and fill in the math in our chart. I've gone ahead and showed you all the work here. And in your chart, when you do your problems, you can really just put the answers here. So we can actually have the answers here, here. That's really the only thing we need to put in the chart. But I just put the work in the chart today. That way you can see how I got those numbers. Okay, it's pretty straightforward. Okay, now we're going to look at a discharge problem. Here, we're going to basically take a very similar circuit. But in this case, we're going to switch it to 2, so that way we can actually do a discharge problem, okay? So here, steady state value has been reached, 0.02, and then we want to figure out what it's doing at these time constants, 2.5, 5, 15, 20, 30, and 40 milliseconds as it's discharging. So again, first step, set up our chart, and we write our times that we are concerned about in the first column. Our second column will be the multiple of time constant, and the current that we'll have will be in the last column, okay? And then we go ahead and do the same rules here for our calculation. Our time constant, in this case, it's the same because we've gone ahead and used the same values in our problem. So I've got 25 millihenries divided by 5,000 kiloohms, and I get 5 microseconds. And you can see I've gone ahead and filled out my multiple of time constant, okay? Now to fill these numbers in is to figure out the final current. So we're going to take the initial current at its steady state value is 0.02, and we're going to subtract the numbers from that. The final current in this case, and for the discharge problem, is going to be 0 because it's going to be fully discharged. So during the transient state, when it's changing, only a portion of the current is going to be there. Okay, it's going to decay in the exponential fashion just like it actually increased. So we can take a look at this. Okay, we're going to basically go over the same way and trace up to the curve and trace over. Okay, and this is the value that we get. We do the multiplication, but in this case, we have to subtract it from the 0.02. Okay, so if we go through the math here, for a half a time constant, I'm going to go up to the curve. I get 0.42, but I'm going to take the 0.42 times 0.02, and I'm subtracting that from my initial 0.02 value, and I get 11.6 milliamps. For here, for one time constant, I go up and I get 0.632, and I do the same multiplication, but in this case, since it's discharging, I subtract it from that 0.2, okay? And I'm going to get, sorry, that should be 0.02 there, I apologize, okay? And that should be 7.4 milliamps, okay? For 3 time constants, okay, I have the 0.93 from my chart. I'm going to take the 0.93 and multiply it by 0.02, and then subtract that from the 0.02, I get 1.4, okay? And you can see I continue here with the math, okay? I have should be 0.6 milliamps, okay? And then at 6 and 8, it's fully discharged, so it'll be 0. So on the next slide, you can see I've gone ahead and I've done my math. I've filled everything in for you. I got my 11.6 milliamps. I've got my 7.4, 1.4, 0.6, and I'm down to 0. So you can see here that the numbers are highest up at the top, and then they're decreasing as we go down because we're discharging. Okay, so that takes care of those problems with the actual current being stored in the inductor. Okay, now I do want to say a couple of notes here. If we do that same type of problem with capacitors, the time constant formula is going to be a little bit different. Okay, it's going to be C times R. So instead of L over R, we have C times R. Okay, now for capacitors, they do not store current, they store voltage. So we will not have to calculate current. In most cases, we'll have the voltage given to us, so it should be the same. Okay, we're going to set up the same chart, but the last column is going to be for voltage, not for current. And we can use that same generic diagram that I gave you. I made that we can use it for either problem. And just like inductors, after 5 time constants have been reached, we've reached the steady state value and we go to 100%. Okay? Now, the only other thing I want to chat with you about is equivalent inductance very quickly and equivalent capacitance. In some cases, you're going to be asked to find equivalent inductance of a group of inductors. These inductors follow the same rules as resistors. So if I have a set of inductors that are in series, I'm going to add them together. If I have a set of inductors that are in parallel, I need to take the reciprocal of each, add them up, and take the reciprocal of the sum. If it's a combination, we're going to use the same rules. So it might be a combination of these two rules. Okay? Now, for equivalent capacitance, okay, we also have to consider that. You could be asked to find the equivalent capacitance of a group of capacitors. These are reverse. These are backwards from resistors. So if I have capacitors that are in parallel, I add them together. You see the difference there. Be careful. If the capacitors are in series, I've got to use that reciprocal rule. If there's a combination, I've got to use a mixture of these two, okay? Now, on the last slide here, when you open this PowerPoint up, if you need some additional help, there's 2 really good videos here, YouTube videos, that will show you guys how to actually do the current and the discharging of a capacitor, okay? Hope that helps. Please watch this video as you need it.